Imagine gazing at a distant star cluster. You observe that some stars shine brightly, their light unwavering. Others flicker erratically, their brightness changing over time. In the vast universe of data, a similar phenomenon can occur. This is called heteroscedasticity. Heteroscedasticity, a term that might sound like it belongs in a science fiction novel, refers to the presence of unequal variances in the errors of a regression model. In simpler terms, it means that the accuracy of our predictions varies across different levels of our independent variable. Just as the flickering stars exhibit unpredictable fluctuations, heteroscedasticity introduces uncertainty into our statistical models. Why does this matter? Imagine trying to predict a star's brightness based on its size. If our predictions are more accurate for smaller stars and less accurate for larger ones, we have a problem. Our model is no longer reliable across the entire spectrum of star sizes. Heteroscedasticity can lead to biased and inefficient estimates in regression analysis. It can distort our understanding of the true relationship between variables and weaken the power of our statistical tests. Just as astronomers rely on precise measurements to study the cosmos, statisticians need ways to detect and address heteroscedasticity to ensure the reliability of their models. In the vast expanse of statistical tools, the Goldfeld-Quandt test stands out as a powerful telescope for detecting heteroscedasticity. Like a cosmic detective, it helps us uncover hidden patterns of unequal variances in our data. Named after Stephen Goldfeld and Richard Quandt, this test provides a simple yet effective way to assess the presence of this statistical anomaly. The Goldfeld-Quandt test is based on the idea that if heteroscedasticity is present, the variance of the errors will be different for different ranges of the independent variable. By dividing our data into groups based on the independent variable, and comparing the variances of the errors in each group, we can determine if there is evidence of heteroscedasticity. This test is particularly useful when we suspect that the variance of the errors is related to the magnitude of the independent variable. For example, if we are studying the relationship between income and spending, we might expect that the variability in spending is higher for individuals with higher incomes. The Goldfeld-Quandt test can help us confirm or refute this suspicion. Just as astronomers use telescopes to peer into the depths of space, statisticians can employ the Goldfeld-Quandt test to examine the intricate workings of their data. By identifying heteroscedasticity, we can take steps to mitigate its effects and ensure the accuracy and reliability of our statistical models. Before embarking on our cosmic journey with the Goldfeld-Quandt test, we must first establish our celestial coordinates. In statistical terms, this means formulating our null and alternative hypotheses. These hypotheses serve as our guiding stars, helping us navigate the complexities of data analysis. The null hypothesis, often denoted as H0, is our starting point. It posits that there is no heteroscedasticity present in our data. In other words, the variance of the errors is constant across all levels of the independent variable. It's like assuming that all the stars in a cluster shine with the same steady light. The alternative hypothesis, denoted as HA, challenges this assumption. It proposes that heteroscedasticity does exist, implying that the variance of the errors is not constant. This is akin to suggesting that some stars in the cluster might flicker or shine more brightly than others. Our goal is to use the Goldfeld-Quandt test to gather evidence and determine which hypothesis is more likely to be true. If the evidence strongly suggests that the variance of the errors is not constant, we reject the null hypothesis and conclude that heteroscedasticity is present. Formulating clear hypotheses is crucial for any statistical test. It provides a framework for interpreting the results and drawing meaningful conclusions. Just as a spaceship needs a clear destination, a statistical test requires well-defined hypotheses to guide the analysis. Section 4. Order from chaos. Sorting data to unmask heteroscedasticity. Imagine trying to study the stars in a chaotic, swirling galaxy. The sheer number and random movement of stars would make it nearly impossible to discern any patterns. Similarly, when dealing with data, we often need to bring order to chaos before we can uncover hidden relationships. The Goldfeld-Quandt test requires us to arrange our data in a specific way to detect heteroscedasticity. The first step is to sort our data points in ascending order based on the values of the independent variable. This is like arranging the stars in our chaotic galaxy according to their distance from Earth. By ordering our data, we create a structure that allows us to see if the variance of the errors changes systematically as the independent variable increases. If heteroscedasticity is present, we would expect to see a pattern in the spread of the data points around the regression line. For example, the spread might be narrower for smaller values of the independent variable and wider for larger values. Sorting our data is a simple yet essential step in the Goldfeld-Quandt test. It allows us to visualize the potential presence of heteroscedasticity and sets the stage for the subsequent steps of the analysis. Just as astronomers use telescopes to bring distant stars into focus, statisticians use data sorting to reveal hidden patterns in their datasets. Section 5. Dividing the universe, splitting data for the Goldfeld-Quandt test. In the vastness of space, astronomers often divide the sky into different regions to study celestial objects more effectively. Similarly, in the Goldfeld-Quandt test, we divide our ordered data into groups to compare the variances of the errors. The standard approach is to split the data into 3 groups, 2 outer groups, and 1 middle group. The middle group is typically excluded from the analysis as it represents the transition zone between the 2 extremes of the independent variable. The size of each group should be roughly equal to ensure a balanced comparison. This division of data is crucial for the Goldfeld-Quandt test. By focusing on the outer groups, we isolate the regions where we suspect heteroscedasticity might be most pronounced. The middle group, often referred to as the excluded observations, serves as a buffer zone, minimizing the influence of any transitional behavior in the data. The specific method for splitting the data can vary depending on the sample size and the nature of the data. However, the underlying principle remains the same: to create distinct groups that allow for a meaningful comparison of variances. Just as astronomers use constellations to divide the night sky, statisticians use data splitting to partition their data and uncover hidden patterns.